Hello everyone, I'm Wenbin Jiang from Baidu. I'm glad to introduce our work, Multiview Classification Model for Knowledge Graph Completion. This is joint research of Baidu and Beijing Jiaotong University. First, I will briefly introduce the background of knowledge graph completion, then describe our multiview learning method in details, and then give the experiments and conclusion. Knowledge graph is a graphic knowledge representation method. A knowledge graph contains a set of triples, where each triple indicates a simple fact. A triple contains a head entity, a tail entity, and a relation connecting them. The relation indicates the relationship between the two entities. In many high-level artificial intelligence problems, knowledge graphs are valuable external resources. For example, in question answering, knowledge graphs are used as the knowledge sources. In recommendation, knowledge graphs provide connecting information between users and items. However, existing knowledge graphs are far from completed, even for the well-known knowledge graphs such as Freebies and WordNet. There are still many missing facts. Therefore, many efforts have been devoted to the problem of knowledge graph completion. This task aims to predicting missing knowledge in the knowledge graph, such as missing relations, entities, and triples. Previous methods on knowledge graph completion can be roughly divided into two groups: embedding-based methods and classification-based methods. Embedding-based methods evaluate candidate triples based on embeddings of entities and relations. Classification-based methods learn a model to directly evaluate the validity of the candidate triples. Here, we give some famous models for both of the two groups. Overall, most of the previous methods perform single-view prediction. Single-view means that it resorts to single-distance metric or classification schema, and uses only the information inside the candidate triples. It is a natural idea that different learning views can be integrated for better KGC performance. Now, let's go to the multi-view learning. For knowledge graph completion, the fundamental problem is to define a triple evaluation function. It maps the input triple into a real number. The real number indicates the validity of the triple. There are four learning views for triple evaluation. The figures below show the learning views. The red node is the head, the green node is the tail, and the edge between them is the relation. The question mark indicates the missing entity or relation. Figure A indicates the prediction of tail given head and relation. Figure B indicates the prediction of head given relation and tail. Figure C indicates the prediction of relation given head and tail. And Figure D indicates the prediction of the validity given all the three components. The context of the candidate triple is also used for prediction. Here, the context is the subgraph surrounding the candidate triple. Each learning view corresponds to specific classification instances. G+ denotes positive instance generation, and G- denotes negative instance generation. The function f retains a randomly corrupted triple not in KG, and the corruption operations include replacing head, replacing tail, or replacing relation. The function g extracts the context subgraph of the candidate triple. The subgraphs can be processed by graph neural networks or by transformer after linearization. These instances are used to train the submodels corresponding to the learning views. Note that in each learning view, we generate multiple negative instances for one positive instance. Given the trained multi-view model, the evaluation of a candidate triple is the summation of the four learning views. For each view, a feed-forward function f processes the context of the positive instance and gives the probability corresponding to the label of the instance. Note that only positive instances are needed in triple evaluation. This is the overall pipeline of multiview learning. The model adopts a multitask learning architecture. Given a candidate triple to be evaluated, it first generates positive instances for all the learning views. All the instances are encoded with the shared embedding and encoding layers, and then classified with separated prediction layers. Finally, the predictions of all the learning views are weightedly integrated to obtain the final prediction. To train the multiview model, we first extract classification instances for each learning view. For training, both positive and negative instances are necessary. The training procedure minimizes the loss over all learning views and all instances. The first sum operation enumerates the training triples. The second sum operation enumerates the 4 learning views. The third sum operation enumerates the positive and negative instances. Finally, for multiview integration, the weights for all the 4 learning views are tuned on the development set. Now, experiment. We use 2 widely used datasets, as described in the table. They fixed the reversible relation problem based on the original version, so they are much harder for KGC. The indicators include mean rank, mean reciprocal rank, and the proportion of valid test triples ranking in top n predictions. Instance generation is very important for the final performance. For the context of each instance, we set the maximum depth of subgraph as 2 and the maximum branch of each node as 3. As described before, for each positive instance, we generate multiple negative instances. We simply select a certain proportion of all possible negative instances for each positive instance. Here, they are the hyperparameters related to the neural networks. The neural networks are implemented in PaddlePaddle, the deep learning platform developed by Baidu. To improve the efficiency of the multiview model, we propose a pre-filtering strategy. It uses a simple classification model to perform pre-filtering, and then uses the multiview model to perform re-ranking. The simple classifier uses the first 2 learning views. Each of them predicts a missing entity based on the relation and the other entity. We can find that pre-filtering strategy works well. The pre-selection of 2,000 best candidates achieves very high recall. The multiview model only needs processing the 2,000 candidates. This table shows the experimental results on the 2 datasets. The multiview model achieves the best performance on the whole, especially evaluated with mean rank. We also find that simple classification also achieves promising results. Okay, let's conclude our work. We propose a novel multiview learning method for knowledge graph completion. It performs candidate triple evaluation with multiple classification views and achieves state-of-the-art performance on 2 widely used datasets. In the future, lots of investigations can be conducted. For example, it can leverage more learning perspectives or resources and use more advanced networks for better context representation and decision making. Thank you for your attention.